Hello everyone. In this video I'm going to talk about the turbines and compressors. We're still in chapter 5 and we already talked about the nozzles and diffusers. So in this video I'm going to talk about turbines and compressors. So turbine is a device that basically drives the electric generators in steam power plants, and the idea behind this is basically we have a fluid that passes through these blades, as you can see in this picture, and this produces some work. So these blades are gonna rotate and they are connected to a shaft, and that shaft produces basically electrical energy. And on the other hand, we have compressors, pumps, and fans. Compressors and pumps are basically the same thing. They're compressing fluids. Compressors are used for compressing the gases to a very high pressure, and pumps are used to compress the liquids. Fans also basically increase the pressure of a gas, but the main purpose of fans are to mobilize the gas. All right, so let's talk about the first law of thermodynamics applied to turbines and compressors. And you can see in this picture, this is a compressor. The air enters from one side, from the bottom basically in this picture, and it exits from the other side, and you can check the pressure, see how the pressure is changing. So at inlet the pressure is 100 kilopascal, at the outlet the pressure is 600 kilopascal. Temperature changes since your pressure is changing, and there is a heat transfer in this specific example, and it also basically requires some work. So compressors, pumps, as opposed to the turbines, require some work input from some basically source. So you can see here that we have a work in, and the purpose of this picture is, for example, to calculate what is the input work. So you can write the first law of thermodynamic for these type of devices. It's basically the same law. You can see it's an open system. The control volume, your system, is the compressor, and you can simply write since this is a steady state flow system, the right side of the equation is 0, so the energy coming in will leave your system, so there is a work in, right? And in this specific example, there is a heat output, so no kinetic energy change, no potential energy change, and then you can basically get into the compressor. So my advice to you is basically to understand how you can play with the general first law of thermodynamics and then apply it to different types of system. So don't memorize, for example, what type of first law of thermodynamics you should use for a compressor, but try to understand how you can utilize the first law of thermodynamics applied to a specific problem. Regarding the turbines, as I mentioned, you can see, let's do an example on that. That's basically the same picture you see there. So what we're going to do in this example, we have a adiabatic steam turbine, and with the adiabatic, you guys remember that adiabatic systems do not transfer heat, so there is no heat transfer here in this system to the surrounding, or from surrounding to the system. And we have a 5 megawatt basically work output. You can see what happens to our fluid from the top, which is the entrance of our system. Pressure is 2 megapascal, drops to 15 kilopascal. Turbine drops the pressure of the fluid, and it basically transferred that energy into the work output, which you can see here in this case is 5 megawatts. The temperature changes, the velocity changes, the height in this case, the elevation of the fluid is changing, so we need to consider that. And the goal is to calculate, for the first part of this problem, is to calculate the magnitude of change in enthalpy, kinetic energy, and potential energy. So the first part is basically to find what is our change of enthalpy. So if you look at the entrance, we have 2 megapascal, 400 degrees Celsius steam coming in. So what you need to do is to basically find what is the state of this thermodynamic state of your steam. So you have to go to the tables and check basically based on this pressure and temperature what is what is the state of your system. Okay, so if you check the tables, you will see basically that at this temperature and pressure you are at, sorry, let me see. Yeah. Okay, at this pressure and temperature you are in a superheated vapor. Try to find it, and if you don't know how to do it, let me know, or so we can discuss basically. So 400 degrees Celsius, 2 megapascal, this is a superheated vapor by checking the tables, and in the superheated vapor we can find that the enthalpy of our system is 3248 kilojoule per kilogram. Superheated tables basically is table A6. Okay, and now at the exit, however, you can see that there is an X given. If you remember, the definition of X is basically the quality. X is called quality, and basically it shows the mass percentage of vapor in your system. So 90% mass wise basically of your outlet fluid is made of vapor. So it's a liquid vapor mixture at 15 kilopascal, and we can calculate the enthalpy by using the equations that we had, HA plus X2 HFG. This is from table A 5 because it's a pressure table, and we don't have the exit temperature, right? So we have to use the pressure to calculate these properties. So you can read the HF from the table, 225.94 plus 90%, and HFG is also from the table, which is 2372.3. The result is basically 2361.01 kilojoule per kilogram. Okay, so that's what you can find from the table, and you can calculate basically H2. H1 is, we already found it, so we can calculate the change in enthalpy of our system. So H2 minus H1, and that's minus 887.39 kilojoule per kilogram. So that's basically one of the parts. The second part of this problem is to calculate, still we are in part A, but we want to calculate the delta KE. Pretty straightforward. This is velocities at the exit or outlet minus velocity inlet squared divided by 2, so 180 meter per second squared minus 50 meter per second squared divided by 2, and converting basically kilojoule per meter squared per second to kilojoule per kilogram is basically 1000 of this. It's pretty straightforward, 14.95 kilojoule per kilogram. Also, we can calculate the change in potential energy of our system, and basically it's gravitational acceleration multiplied by the change in elevation, which is 9.81 multiplied by 6 minus 10. This is 6, this is 10, so make sure you put this is Z2 minus Z1, right? This is 1, sorry, my handwriting. And you also need to convert basically similar to the above. It's basically 1000 meters square second square, 1 kilojoule per kilogram, and that is equal to minus 0.4 kilojoule per kilogram. So that's basically all the part 1 problem. So in part 2, what we want to find is to calculate the work done per unit mass. So for this we need to use the first law of thermodynamic, and since this is a steady state system, let me erase this top part so we can continue writing here. All right, so for the second part, we have to write the first law of thermodynamic. So the first law of thermodynamic for this system should include the change in potential energy, change in kinetic energy, and also change in enthalpy. So if I want to write, this is a steady state problem. So an energy in basically is equal to energy out. So m dot h1 plus v1 square over 2 plus gz1 is equal to, we have also a work, heat is 0, m dot, and m dot in is equal to m dot out, because again this is a steady flow system, plus v2 square over 2 plus gz2. And we have already calculated all these things, so basically we can, from the above equation, we can calculate the W out, and W out is basically equal to, just divide each side by m dot, and that's going to give you minus delta H minus kinetic energy change minus potential energy change. So we already calculated these properties in the previous part, so just substitute the numbers from part A, and what you're gonna get is 872.48 kilojoule per kilogram. So that's part B, and in part C what we wanna calculate is the mass flow rate needed. So it's pretty straightforward again. You have the total mass, the work done, right? And divided by the work per unit mass you calculated in previous part, that's going to give you the mass flow rate. So 5,000 kilojoule per second, that was 5 megawatts, right? And you divide it by work out, so that's basically 872. 0.48, and the result is 5.73 kilojoule kilogram per second. All right, so that's it for this problem. So please let me know if you have any questions, and we're going to continue on some other devices.